Hi, this is session number 11. Take a deep breath. I was just thinking this morning after discussion, someone said, "Why do you call it an ERR file? Wouldn't log be a much better name?" And absolutely, it's much better. So it's sold, and our log files are going to be called log instead of err from now on. There'll probably be other things. If people are watching this on videotape, some months from today, they'll probably be having a listing of TeX82 where the module numbers are a little different, and it'll say, and theirs will say log already, and they won't understand what's going on. I imagine they'll be able to sort this out, make some sense out of a few of the remarks we make anyway, even though TeX is still absorbing these new ideas. Someday it'll be too late to absorb any new ideas, so we got to have all our good ideas very soon. Yeah. Dan? You got an objection to log.
Log does conflict with the TOPS 20 system convention, which is that they're the output of batch files. Do you care?
Oh, I see. You mean if you gave a batch processing thing, it would give you a log file for that too? Yeah, I see. So these three-letter names have been taken. How about LN for natural log? Okay, well, we'll play around with this again in discussion. Okay. The topic of the hour is DVI files, and actually, I'll spend a little bit of time talking about what TeX does as far as generating the DVI files are concerned, but I think I'll spend more of the time just explaining exactly what the meaning of DVI files is. The reason is most of your work is going to be doing something with DVI files, and that's outside the scope of TeX. TeX considers its job is done when it's written a DVI file, but that's when the hard work starts. You have to get it, to make a really good system. You should be able to handle many people wanting to print their DVI files in a big hurry, and you might want to queue them up somehow, send them to a printer. You have to, in order to print them, you have to figure out how to convert the DVI files to whatever the printer wants to see, and combine it with pixel files or something for fonts and so on. That's where the work is, and so you're going to have unless you can find some system that already does this for you. They exist for things like the Versatech and the Canon, and the work doesn't have to be done over and over for every device by every person, but otherwise that's going to be a major part of your work. Is something that isn't really part of TeX82 at all. It's something that goes on after. So you can be sitting there and have TeX82, and it'll do all these great operations and give you a DVI file, and there you'll be sitting with a DVI file. You probably want to know at least what that DVI file contains, and that's what I'm going to talk about this hour. And we also have DVI type, so you can list the DVI file, and it would tell you what the page would look like if you had a printer to see it on. That's about the best we can do with the software that we're giving you on our tape. Okay, DVI file stands for device independent, and this is our goal: is that TeX should be able to produce output that can be used on many different devices. And the drivers have, in fact, been written for lots of devices, and we believe that any reasonable device can be driven by a DVI reading program. That section. Let's see, device independent file format is part 40 of the write-up, and it starts now at module 498, which with the description of the DVI. Now this has gone through 3 generations. The version 0 was the first proposal for DVI. Then, based on the experience gained with that, it came out with version 1. One of the big differences was the way the bytes were packed in words, because most people needed them. For example, on a 36-bit machine, they needed the leading bits to be, the trailing bits to be 0 instead of the leading bits to be 0 when they tried file transfer protocols on these things. And That was one of the major changes between version 0 and version 1. But now, the present conventions here are version 2, which are similar to those in version 1, except that we've added more opcodes and renumbered all the opcodes. So you can't print with you have to change your DVI software slightly. It has the same structure but different numbers to the codes, and essentially the revisions that were done at this stage were to clean things up, fill gaps in the previous thing, and make it sort of complete and more symmetrical, and in an order that looked a little more reasonable. Now, I guess I should go first into the discussion of what the DVI file looks like. It's similar to what we said with the TFM file. DVI file is again a packed file of 8 bits. So it's a sequence of codes 0 to 255. And whatever order you want to put those on your file doesn't matter, as long because we just put it out as a sequence of 8 bits. I guess I could also present one on the screen like we did for the other case, so you can see what they look like on this machine. So let's see. I probably have a DVI file in my directory now. Nope. Okay. Let me see. Excuse me? Well, I think what I'll do is this. I'll use that as the last result, but I'm going to try to run TeX and make a DVI now. So let's see. I'll run any TeX, which is the thing that has nothing at all preloaded. What's going on? I'm swapped out. This never happens at sale. We've got 4,000. We got 4 million words of memory requested by all the users at this point. Okay, well, I got in anyway. Okay, now that's the debugger that I'm talking to, and I better make this a pretty short test program. Uh-oh, TeX pool doesn't match. Tangle me again. So this failed the sum check. What's going on here? Okay, I'll run the preloaded version instead of any TeX. Sorry about this. I'll have to. Anyway, we might as well make up a DVI file. At this point, I have to kill some of the things that are preloaded, because this is trip that's preloaded, and I really don't want that. So. I've got to kill every par, which is set to some ridiculous value that would happen at every paragraph. Now I'll define a new font. Let's say font 1 equals CMR10. And then I'll, I think, just say hello and get out. So, oh, I got to select font 1 too. It's the current font. And then I say hello and get out. So let's try end. Okay, an overfull box. That's okay. Excuse me? You see that where it says hello there? Has a vertical rule after it. That's because it had an overfull box. I made my H size 0, so no wonder it's overfull box. Okay. I didn't set H size to anything. Okay. Now, well, I could print it too. We can go over and see if it says hello on there. But now, anyway, we have a DVI file, and it's called textput.dvi. That's what happens if you don't give a name. If we said last time, if you say input to paper, then your names are paper. But here I didn't give any name, and so. See, I got some mail here too. Okay. So anyway, the default name, if none of that was specified by the first thing you did, is TeXput. Okay, now over in Jack's Hall we could read this message that says hello. Maybe we can see it later on this afternoon. But the DVI file itself is in there, so we can first print it in octal format, and then we can print it in more symbolic form. TeXput.dvi. A bunch of zeros there at the beginning. It's not too long. Okay, that's the file. And now let's explain. So anyway, it looks like that. We'll come back and be able to understand what all those sevens are and stuff in a few minutes. Okay, so that's a DVI file is supposed to be short. It's supposed to be a reasonably compact way to describe printing, and it's also supposed to be easy for a machine to read efficiently. These were designed by David Fuchs, and I think those two goals are fairly well achieved. Of course, this isn't all saying hello. This is mostly overhead that's involved with all DVI files, saying what version number they are and things like that. Okay, the DVI file is best thought of, I think, as an interpretive routine. We could have the lights on now, because I'll just be going on. It's best thought of as an interpretive routine, or at least from the old days, we call them interpretive routines. These were programs that go through and consider that they are defining another computer, and the interpretive routine are the central processing unit of this new computer, and the interpretive routine is really a set of opcodes and operands and so on, something like machines actually execute in their hardware, but we're doing it in software. And the opcode that comes along is the first thing. So the beginning of each byte in the DVI file starts out as an opcode. And then, depending on the opcode, it has certain operands that it expects to follow. The opcodes start on module 500, page 174 of our listing. And the first opcode is a very simple one, set character 0. It's just a 0. So if our DVI file has a byte of 0, this is going to mean typeset character 0 from the current font. We wouldn't give that first. We'd better set up a current font, because the current font is undefined when we start. The machine that we're simulating here, or defining in this DVI machine, has a few registers. One of them is the font register F. It's an integer. Font numbers can be anything, any 32-bit numbers. So this will handle quite a few fonts. In case now TeX will never generate, however, for a font number larger than the number of distinct fonts it handles, which is some quarter word. So typically we would never get a very large font number ourselves, but DVI is defined to allow large font numbers, because TeX isn't the only system producing DVI files. Then we also have a current position on the page, and that's H and V, the horizontal and vertical coordinates on the page. It's just like Cartesian coordinates, except upside down. That is, if V gets bigger, we move down instead of up. But H gets bigger, we move to the right. So H and V are these things, and 0 position is the upper left corner of the page. We start on every page at 0, and with the current font undefined. Then we have 4 other registers called W, X, Y, and Z, and these are used to keep track of spaces that we're going to be using over again. When we skip around, typically the amount of space that you move is repeated, and so we can save space in the DVI file by not repeating the information over and over again. W and X are 2 registers for horizontal units of spacing. Y and Z are 2 registers for vertical units of spacing. Then we also have a stack built in our hypothetical machine, and the stack contains values H, V, W, X, Y, and Z. These other registers get pushed down and popped up at various times, so that we can in one byte we can say push and one byte say pop, and thereby change a lot of these values, go back to a previous state. The current font is not pushed and popped, and this is really because it seems to be better not to. Now, all of these things are 32-bit numbers, including a sign. So we go minus 2 to the 31 up to plus 2 to the 31 minus 1. This is a 2's complement type of a thing, and there's they're given as when we say spacing H and V, we mean in terms of something, some unit of measure, of course. Now, the unit of measure in version 1 DVI files was called the RSU, for ridiculously small unit. It's intended to be such a small unit of measure that rounding errors don't matter. If you accumulate 1,000 of rounding errors and you're off by 1,000 RSUs, the eye still won't see it, or maybe 100 anyway. Impossible to notice. Well, the actual unit of measurement, though, is not defined particularly. We don't call them RSUs anymore in this new report. But there's a conversion factor at the end of the DVI file, two numbers, the numerator and denominator, that says if you multiply by the numerator and divide by the denominator, then you get units of, I think it's 10 to the minus 7th meters or 10 to the minus 8th meters, something like that. So it's basically we do have a metric system involved here. And TeX always sets those numbers to the right value so that the units that TeX outputs is scale points, same as TeX uses everywhere else in its internal conversion, which is pretty ridiculously small unit. So scaled points is now 2 to the 16th of them make one printer's point, is rationally converted by a certain fraction into the metric system in case for other programs writing DVI files would find other units to be appropriate. Okay. Now the DVI type program shows in great detail, that's one of these things in the TeXware book, shows in great detail how we recommend rounding positions in the DVI file to low raster devices. I probably should meant to talk about that a little bit later. But you see, we have two kinds of units. We have these ridiculously small units, which we're going to be giving our measurements in the DVI file, and then you have pixels, something on your actual device, and you have to convert between the one and the other. The proper way to do it is to keep most of your arithmetic in the DVI units and do rounding to pixels at key times, like at the beginning of a word, something like that. Okay, now if you want to typeset character number 0 from the current font F, you just give byte 0, and what could be more compact than that? I mean, okay. Similarly, 1 up to 127 will typeset characters 1 through 127 respectively. Now, we couldn't do this for all 256 characters in the font because we only have 256 opcodes. And so if you have to set a character number 128, you do it in 2 bytes, and there's a instruction set 1. This one's called set 1, which is followed by the character that you're supposed to set. And so in the notation in the book, it says C bracket 1. In the brackets is the number of bytes that we assume the operand is. 129 is set 2, which is C2, and 130, these are not generated by TeX82. This would be to set 3-byte and 4-byte characters. There's even a set 4. So all of these possibilities. Set 4 would say so if I gave 131, then it would say read in the next 4 bytes, and then whatever those 4 bytes are, that's the number of the character that you're supposed to set next in the current font. So we can handle fonts with 2 to the 32 different characters in them. The DVI format is not tried to be restricted. It's supposed to be useful for even things. Now, also, people might use this somehow. They might have some convention for these bits, like this reflects the color or something like that. Who knows? But TeX will only output C1 for the characters 128 through 255. Okay. Now, this is typical of the commands in DVI, that there will be versions 1, 2, 3, and 4, depending on how many bytes you need for the operand. So that the command will tell you. So if you only need a 2-byte number, then you use the opcode that says so. That only 2 bytes are needed afterwards. So this is a 2-byte total command, one for the opcode and one for the character. This would be a 5-byte total command. Question? No? Dave? What? Now, all of these characters, all of these set instructions, not only typeset the character, but they also move H to the right by the width of the character. So this is set character 0, and H is set to H plus the width of that character. So the DVI reading programs have to have access to the width information for each character, just as TeX does. And so DVI reading programs will use the same sum check that TeX had in order to make sure that it makes the same assumption. Because TeX isn't going to tell the DVI file how wide that character is. DVI reader is supposed to get that out of some other thing. Now, we put this information also in the pixel file so that the DVI reading program doesn't have to read both TFM file and pixel file. And so Metafont will put this information out twice with the same sum check, so that you can make sure that your information is consistent. But this is important for keeping the total length of DVI file down. Okay. Now, there's also a set rule character, which is 132, and this one is followed by 2 operands, A and B, each 4 bytes long. All 4-byte long parameters are signed. That means that if you have a 4-byte long parameter, the first it could be between -2 to the 31 and so on, looking at the first bit as a sign. However, in these 1 and 2 and 3-byte characters, it's always plus. So the range here is, for example, in set 2 is 0 to 65,535. You don't have a negative character number for these, but a 4-byte number is always considered to be signed, so that we don't overflow the constraints of a 32-bit computer. We're supposed to be able to read this on any 32-bit computer, which would want a 4-byte number to be considered a signed integer, I guess. And the set rule instruction is like set char, that it also will advance H after the rule is done. Now A is the height and B is the width of this rule. And if the height is 0 or the width is 0, then we don't do anything except move by B. Similarly, if any of these are negative, so if B is -5, for example, we wouldn't put any rule there, because what's a rule that's -5 things wide? It's kind of invisible, or you could imagine tearing a hole in the paper or something. I don't know, but it will move H, and H will decrease by 5 in that case. Now, there are rules specified in the TeX82 manual, so that the rules. There are things in this manual that say how we could get consistency between TeX and Metafont, so that if somebody designs a character using Metafont and has certain conventions about how that he's drawing a straight line in his character, and then we have a DVI command that sets a rule, we can guarantee that we're going to line up the pixels perfectly so that the rule have the same number of pixels high as the other, and those are spelled out in the book precisely. So it should be possible to have consistency across these things without no matter what the rounding conventions are. So we designed the thing with that uppermost in our mind, that we should be able to ensure perfect alignment. This is important, for example, embarrassing cases. If you have our large radical sign now actually has a little bit of a top to it, because otherwise on such a large case it would look bad if your variable was too close to it. So we give this extra space in the radical sign itself. Well, then TeX is going to put a rule next to that, and the positioning says that the baseline of the square root sign is exactly the same as the baseline of the rule. This means TeX computes the same number for both of these, and they're given in precisely the same DVI coordinates in terms of V here. So they'll be exactly the same height V above the line. This rule will be set by exactly the height of this character, and therefore we should get exactly the same output if the DVI servers are implemented properly. This should be exactly as thick in terms of number of pixels. Even if we move this up on the page 1/3 of a pixel, the rounding should have been exactly the same for both calculations, for this one and this one. It wasn't true in the present version of TeX, but we get positive alignment in the other version. This, by the way, big square root would be an extensible character, but the top part has this feature. Set rule, I might mention, goes up above the rule starts at the lower left corner. The current position HV is the lower left corner of the rule, and then so this is your reference point, and then you move H to the width of the rule afterwards. Now, corresponding to these set commands, we also have put commands, like 133, I believe, is put 1. I won't write them all out. Partly I don't have room for it. Put 1 followed by a 1-character code, and the put commands are just like the set commands. Like this would put 1 was like set 1. You give a character code that you're supposed to typeset. The only difference is that H doesn't change. This is when you're setting characters above each other. For example, you might like to do that if you're doing an extensible character like this, and just put out the pieces, the replicating pieces. However, I don't think TeX82 actually generates that command because we don't have character nodes in vertical mode. So there's put commands and put rule and so on. All right, the operation 138 is a no-op. It does nothing, and it just in case for some reason you want to fill space or blank something out, it's something that TeX doesn't generate. But you can have these between DVI commands if you want them for some reason or other convenient to your software. You can't put a no-op in the middle of a program. It has to be between commands. You couldn't put a no-op between a set 1 and its operand. How would you know that was, that it wasn't supposed to be character number 138 that you were doing there? But you can put it between commands, all right. Okay. Well, anyway, I don't have to give these numbers anymore. Let me just give the mnemonics. So no-op, and then there's not, bop, and eop, and pop. Well, push comes before pop, but there's a lot of these that seem to rhyme. Bop is beginning of a page, and this is the long one. It's followed by 11 parameters, each 4 bytes long. We don't expect this happens very often, typically, but it's followed by C0, 4 bytes, up to C9, 4 bytes, and then by another 4-byte parameter, P, which is okay. Now, P is a pointer to the previous bop in the file. And if it's the very first bop in the file, P is -1. So this allows you to go backwards through the file, skipping back pages from the end of the file back to the front. And we use this on some machines. I think on the Canon they use it, for example, because the paper comes out and you would like it to be stacked, so that it's better to print the last page first. Otherwise, after you get your output, you have to go like this to get them right. So they read the file backwards. And isn't that right, Jan?
Yes.
It takes so long to pick up the microphone. Man, a few words. Okay, we got this allows you to go back through the file to P to the previous bop. Okay. Beginning of page. The C0 through C9 are the values of TeX, are cross-reference values that a person can use in order to identify a page location. And TeX puts out the values of the first 10 counters, count 0 to count 9, for this purpose. So you can identify a page by its counter. Now, what you usually get on your screen is just the value of count 0. But sometimes people like to, will have more substructure to this, and so David wanted to be generous, so he put 10 of them out. I don't know if anybody's ever used more than 3, but our convention that we've been using with some success has been to print them out with dots. For example, 1.2.1 would be a page where count 0 is 1 and count 1 is 2 and count 3 is 1. And then when we give the starting page command on say we'd like to start at a certain page, if we said 1.*.2, this would mean find the first page that has the form count 1 is 1, count 0 is 1, count 2 is 2, and count 1 we don't look at. Then it would print out. It also, depending on how many dots we got, it would print out that as it's printing on the console of the printer. It would say I'm printing page something, and it would give the first 3 counts if I specified that. If I specified in my starting, if I said my starting page number was 1*2*, then it would give me 4 counts to show what page it's at. This convention seems to work out reasonably well for displaying page numbers as you're doing it. You have a question?
I wanted to ask, do you have one bop for each ship out macro that's involved?
One bop for every ship out, exactly. So ship out puts out a bop and an EOP, which is end of page, right? Mm-hmm. So now, when you give a bop, it starts out, initializes all its registers to 0, and the current font is undefined, and the stack is empty. You're supposed to push and pops are supposed to be all contained before you get to the EOP. So the stack should be empty when you get to the end of page. But the end of page is a time when you print everything. Now, in most cases, when you're implementing this, you'll be doing EOP. You'll be doing a lot of computation at the time of EOP that's not reflected in my DVI type program. Because for most devices, you have to sort the information into order by some coordinate or other, either horizontal or vertical or something. Now, the things that you get out of TeX are not guaranteed to be in any particular order. They tend to be in order, but not always, because subscripts and superscripts, for example, or people doing for funny things with negative glue could certainly, the order that comes out in is somehow what we would call pre-order in computer science. As far as the list structure is concerned, we just unwind the list recursively and take things as they come to us. That tends to be in order, and that tends to help sorting routines, but TeX doesn't do the sorting itself. That's the responsibility of your DVI reading program if you need to sort. Some devices don't need it, some devices do, but what you typically do is you get to a bop, and then you start looking at the rest of the bytes and this gives you coordinate positions and characters, and you start building a table, and then when you get to the EOP, output that table. We also build in protection against overflowing the table. So if the table gets too full, then we sort it and output that part of it right there, and then continue on with the next part of the page too, and sort each part. We will break up this information if we have to on our alpha type serving things. This turned out we didn't need it until people started using our programs for VLSI layout. And so right now, for example, when you get a Sun workstation, it was printed because of DVI files and TeX and our software for driving the typesetter, because the masks that were made for some of the boards were done with software that had a huge number of commands between BOP and EOP. Okay. Now push says take your stack and your HV, WXYZ registers go onto the stack and on top of whatever was there before. You don't change any of their values. And POP takes the values from the stack and puts them into those registers, forgetting what the other registers were. And typically, why would you do that? Well, it goes something like this. Most pages, we might say, consist of lines, and so the page is a vertical list. And then when it comes to this point, then it gets to the baseline here, and then it says push. And now it goes into a horizontal list and starts moving across this way. Well, when it says pop later on, we're right back here. Then we can do a vertical motion, gets us to here. We push again and do this kind of computation. At the end, this vertical motion will be the same as that one. So we've recaptured the previous value. We don't have to. Push is pop is a fast way to back up to where you were before. You see. Helps a lot with leaders and other things too that would tend to fill up these DVI files. Okay, now the other commands are just for motion primarily, and there's so many of them. They fit into a simple pattern. This is write 1, write 2, write 3, write 4. I'll just say write 1 as a representative of this class, and it's followed by an amount of horizontal motion B. Now in this case, B is assigned quantity. So this is between minus 128 and less than plus 128. In these commands where we're talking about motion, we use a sign number. So right might actually send you to the left. And the same with write 2, write 3, write 4, depending on how many. Write 1 is actually rather uncommon because these DVI units are so small that we would have to move at least 200 or something in order to see it. But it could happen. But usually write 2 is in the ballpark of the kind of motions that we'll actually be making. And since the set character commands already do the rightward motion, most of the time this will be moving from word to word or just doing a little kerning between letters of the word. Then there's W0, W1 to W4, and interestingly, the definition of the write command, it does two things. It says H to H plus B, and it also sets W to B. So the amount that you move by is saved in this register double. Oh, wait a minute. No, that's not right. No, I'm sorry. It doesn't do anything. Sorry. W1. W1 is a command that sets H to H plus B. There's a B1 associated with this guy. H to H plus B and W to B. And similarly, W4 is followed by a 4-byte parameter and does the same thing. Now, W0 just sets H to H plus W. So that whenever we have the right amount of motion already in register W, then we get by with a 1-byte command. And TeX has a neat way of that seems amazingly effective in producing 1-byte commands on the examples I tried. it learns the kind of spaces that you're making. And the type, and in normal text, each line typically has 1 or 2 spaces that are there, one for kerns and one for between letters, between words. Math formulas have another kind of spacing that goes around the operators and things like that, but this seems to learn them very quickly so that we can get by with 1-byte commands quite often. There's X0 through X4, same deal, but using X instead of W. We have these 2 registers. Each one can be used. There's no, the present version of TeX uses W only for space between words and X only for kerns, but TeX82 has an algorithm that tries to be clever in assigning these, and so you can't assume that just because it's an X that it's either a kern or something else that generated it. Now, similarly to the right in W and X, we have down, Y, and Z. Exactly the same, except you replace horizontal by vertical motion in all the commands. So that takes us up to operator Z4, which is 170. We still got up to go up to 255 possible opcodes. Well, the next 64 of them are all to change current font. So 171 is set font 0, and or font num 0, excuse me, so is the official name, FNTNUM, and up to whatever 234, which is font num 63. This command sets F to 0 and F to 63. That's all it does. But we got set the current font number, and then we have font 1, 2, 3, and 4 for font numbers of 1 byte, 2 bytes, 3 bytes, 4 bytes. So if we now TeX assigns its fonts internal codes, and the first font that you name will get number 0. Or actually, internally it'll get number font base plus 1. But this will convert to 0 in the DVI file. And so only if you've given more than 64 distinct fonts in your job will you ever need this command 235, which is the FNT1 instruction, which is followed by a 1-byte font specification. And you could have anything up to 4 bytes. One proviso is that you're not allowed to declare font number -1. Font number -1 is the only one you're not allowed to have. Well, there's 2 more opcodes, and then it's done. Font 4 is 238, so 239 is XXX. This is what comes out of the XSend instruction, and so people will be interested in this for extensions to TeX. When somebody says XSend in TeX, XSend, and then you give something here. This is expanded as if it was in an XDEF. Any macros are expanded in this text, and the resulting characters are placed after an XX command in the DVI file associated with the current H and V where you are, where this XSend appeared in the paragraph. And it's followed by 1 byte that tells how many bytes are following, and then by the text in TeX internal ASCII code that's m bytes long. Now here, if people feel strongly, well, okay, somebody suggested the other day that he doesn't want to restrict this m to 255, that he would like to be able to have XSend of a huge long piece of text coming out here. But right now we're restricting it to 255 maximum through XSend. Now my inclination right now is that if you want to send a large amount of information, your best bet is putting it in a file and naming that file here. If there's a strong call that we need really an XXX2 instruction that will take a 2-byte M, and then we could go up to 65K bytes. I wouldn't imagine wanting to stick more than that into the middle of a DVI file for sure. Then what we would have to do is change the few programs that we already have reading this version of DVI. If a change is ever to be made, it should be made now, because it could be done by a few people in a few minutes before this gets frozen. But next year it'd be very difficult. We'd have to say that's DVI version 3. And so we still have a time to make such a change. It's the only idea I've ever heard of that might be useful for putting into present DVI file. So you might think about that and give me some comments on it after. Yeah, well, right now we just have XXX limited to a maximum of 256 bytes in this XN. The last opcode is 240, which is the postamble. And that's the strange part of DVI files, which I'll be talking about soon. Opcodes 241 to 255 aren't defined, and so it wouldn't be that hard to switch in XXX1 and XXX2 there. We still have a few left for future use, and no really great ideas as to what to do with them. Roger?
Yeah, on the current DVI you have a trailer byte of some sort that comes after the postamble, and I don't see that in this list.
That's
I think
true.
It's a 223 in DVI.
Yeah, I'll talk about that. That doesn't it only has meaning at the end of the postamble. So it's so that's okay. Now the postamble is so if we're reading from the front of the file, we get to 240. This should occur only right after an EOP, after end of page. We should never run into a bare postamble. However, TeX generated one the other day, and I found out why. I think it was in the middle of a "this can't happen" error. So it didn't get to the end of a page. The "this can't happen" error occurred in the middle of the DVI, in the middle of a ship out. So it terminated right away, but in order to close out the DVI file, it wrote a postamble. So so it is possible, to generate this, and the DVI reader would reject the file then when it got there and saw a postamble right in the middle of a page. Now, the postamble is one of the words that we had to make sure that we could hyphenate, because it doesn't appear in the English language dictionaries. And in fact, the present TeX hyphenation management calls it a postamble. So we had to put it in that list of words that you looked at, that was there yesterday, to get it hyphenated properly. It's a coined word, but it means that we're giving information that comes after instead of before. But we really read it first. We need the information first, but TeX doesn't know it until the end. So now the alternative of saving enough room at the beginning of a file for it was worse than what happened. So David had this neat idea, and it seems to be working fine, to put the information at the end of the file. And so at the very end of the file comes this postamble, which is a huge long list of information. It's in module 503 of your book, tells you what it is. I'll just read it to you. The first thing after the PST is 4 bytes. That's the pointer to the final BOP in the file. So this is if there weren't any BOPs at all, you get -1 there. But this is where you can start going backwards through the file. Then comes the numerator and denominator that I told you about, telling you what your DVI units are, defining those. And then comes, M, which is the magnification parameter. So person in TeX said magnify 2000. There you're going to get the number 2000 here. This is something that is supposed to be applied globally throughout the entire file after everything else has been said and done, also magnified by this amount. So effectively it just goes in with the numerator and denominator, and the true calculation to convert DVI units to these 10 to the 7th minus 7th meters is m times n divided by 1000d. That's the factor that's used. We generally compute that in floating point arithmetic. Now, magnification passes through only in that way in TeX, unless you say ask for true dimensions. You can ask for true inches, true points, or something in a dimension in TeX. And if you ask for say 2 true inches, and your magnification was 2,000, then TeX would convert that to dimension to 1 inch, so that later on when you magnify it, you get 2 inches. But if you haven't said true anywhere in your TeX file, then the only effect of the magnification parameter is to change this thing in the postamble that comes out here. When you write DVI software, it's also a good idea to provide the user with, in many cases, it's a good idea to provide the user with a chance to override the magnification option at printing time, and say, just don't, pretend that the TeX job said to magnify a little bit more, so that you don't have to rerun the TeX job. Just can say, okay, spool this at 50% larger. If you have the fonts at that size, you can do it. Some people asked about storing fonts at different magnifications. Since we can say CMR10 at 15 points and CMR10 at 20 points, that means that we should have in our font library these options, perhaps. And how to name them? Well, it depends on the system you're using. The Dover software requires a certain naming convention that has quite a lot of structure, but on other systems, like when we use the Canon, we work with just the ordinary file system in our computer, and a file that's been magnified to 4,000, for example, gets a suffix. It'd be called CMR10.R40, and at 10 point it would be called .R10. And so the server just looks for a font file or pixel file with a suffix that matches the amount of magnification. On our alpha type, we use more digits than that, but it's something like that. We say it's an ant file for the alpha type, and we call it the suffix on. It would be something like 1,000 ant for a normal font, and 1,200 ant for a font that's been magnified 1,200, something like that. So we just put in the extension of the file name, the indication as to if these pixels were generated at a different size from the other one. What we do then in our software is we find the smallest size greater than or equal to the one that we're supposed to print at, and then we try to shrink it down if we can with the printing hardware. If we can't do that, then we complain and say, well, we had to substitute a font. We try to substitute the closest we can. That's the kind of issue. Anyway, magnification is this next thing in the postamble. Then there's L and U. L and U are the measurements of the tallest page, the height plus depth of the tallest page and the width of the widest page. So when we start typesetting a page, we start at the upper left-hand corner. L would represent the maximum height and depth of that page. U is the, I couldn't call it W because W is one of the registers of the DVI machine. So L is the maximum of all these numbers. U is the maximum of all these sizes. However, this does not tell you where the characters really are. I mean, somebody might have had an overfull box that sticks out here, or done backspacing or something on the margins, and there might be characters outside these things. This is just the box, the size of the box, like it was a V box with a certain height and depth. The maximum size of boxes that were shipped out, but it's not actually computed by the position of things in the box. And these numbers, the purpose of these numbers is so that you might want to put in your spooling software something that tries to lay things out on a piece of film. And we wanted these things to like if you can fit four of these pages on one piece of your medium that you're printing on, then you could save those tend to be expensive on some prototypesetters, so you could pack the thing yourself. But we never really have implemented that yet. We just put L and U in for that purpose. So, we've got other ways of specifying. The user gives us a option file that tells where to put the pages for a particular job. Each job has its own option file in that way. Now, let's see, I covered L and U, then comes T, S and T. S is I think the greatest, the maximum stack depth. It tells how big a stack you have to have in order to handle this DVI file. And T is the total number of pages in the file, just in case you wondered. Total number of BOP commands. After that is the all-important font definitions. And TeX will only put out the font definitions that are actually used. If you've declared fonts but never set any characters from the fonts, it doesn't come in the file. And the font definition consists of the internal font number so that you can match it. It's like font number 0 through 63 typically. Then you got a checksum for the font so that you can do checking, make sure that you've used the same information that TeX did when it generated this file. You got an extra scale factor for the font. This substitutes for the design size of the font. And then you've got the area, the font area, and the font name that are just passed to you, and as an ASCII string. We do this for each font, and then we have a -1, 4 bytes representing -1 to tell you that you're at the end of the fonts. And that's why font code -1 was not allowed, because as soon as you get to a -1, then it's in. Now after that font number -1 we're reading on module 504, then we got a pointer to the postamble command. So let's see if I can make a little picture of that. My DVI file is going along, and I've got a -1 sitting there, and then I've got a pointer to the postamble command, 4 bytes that give the address of the postamble command where it appeared here. After that comes the identification byte, which is 2. So this is version 2 DVI file. And then we've got any number greater than or equal 4 bytes that are all equal to 223. Now I got to let you in on a secret. 223, if you put it in hex, is DF. And David Fuchs is the one who designed DVI files. I believe it's a little too much of a coincidence. So we call this the signature bytes of the DVI file. And he put at least 4 of those in there. And this is to make it possible for if things are packed 4 bytes to a word to find the end of the file by means of routines that exist on most systems. Now, standard Pascal doesn't allow you to start reading a file at the end and do random positioning going back through the file, but most systems do allow you to do this. And if you don't have such a system, then you start at the beginning and zip up to the postamble and then start at the beginning again and start your typesetting. But in most systems you can get it from the back, so you come back to the end of the file, read back over the 223s, check that you got version 2, then this tells you where the postamble is. The postamble tells you where the previous BOP is if you want to go backwards, or you can go back. But anyway, you can read all the fonts here and do the checking. The DVI type program that we've distributed here includes both options, and you can see the code that would read the file in both directions. Time is getting short, but I would like to run DVI type on this file so you can see what it looks like on a reasonable file. So let's go back to the computer and see, and this was called textput.dvi, and I'll output to textput.type, let's say. Okay, now it's going to ask me for several levels, for several things, and it also says I can type question mark for help. 2 for a complete listing, 0 for errors only, 1 for something in between. I'm going to get 2 for a complete listing. The starting page I can use the default. If I said star dot star, however, I'll show you that just will print out both count numbers, count 0 and count 1, both of which happen to be 0, I guess. Maximum number of pages is, I'll just type, I'll just allow it to do 1,000,000 pages if there are that many. Then it will convert things to pixels per inch. And if I want points instead of, if I want points, there's 7227 points in 100 inches, so I'll type 7227 divided by 100. The magnification, I can just say return to keep the old magnification. On any of those, I could have typed help, and now it's done it, so I can look at the file, textput.type, and this should be the DVI file that we created. Got to move it over to the right again. Okay, so it told me the options that I selected, and the postamble starts at byte number 68. The bytes are numbered starting at 0. Gives me the numerator, denominator. Magnification was set at 2000 because of the trip file actually set magnification 2000. So things are getting magnified twice. We loaded font 3, CMR10 at size 10 DVI units, but that actually will be magnified. Okay, now because the DVI units are magnified. Okay, so byte number 0 was the beginning of page 0.0. And if I had said star dot star dot star dot star, then I would have seen all the counters of that page. Then it says down 3, 4, 5, 5, 1, 1, 1. So the vertical the register V is moving down the page by 455,000 DVI units. It has a warning here. Says the absolute value of V is greater than 0. What? I don't understand that at all. I have to think about that. What's so bad about that? What? No. Huh? Do you think so? That line is complete. Okay, well, that doesn't seem... You had an overfull box. Oh, I see. Yeah. If you look up here, it says max V equals 0. You see, that was the max V is the largest, supposedly largest V that you've got, and this is warning me that I've exceeded that with some characters outside of there. Okay. Oh, thank you. So then I push and get my first box, and this comment here that I'm at level 0 of the stack has the following values of H, V, W, X, Y, and Z. The double H and double V are rounded to pixels, which in this case is rounded to points. So I'm 14 points below the upper corner of this thing because of probably the baseline skip, which I'm not sure what it was. Must have been 7 points, something like that, for the top baseline. Then at byte 50 of the DVI file, I selected instruction font num 3. So I picked up font number 3. Font numbers 0, 1, and 2 were preloaded to be those trip fonts that I didn't actually use. So the current font now is CMR10. In byte 51 of the DVI file, I'm setting character 72, which is ABC, which should be a capital H for hello. And you see down there in brackets, there's a comment. If I hadn't asked for level 2, which gives me everything, I would have just seen hello. I would have gotten a much more terse description from DVI type. I've asked for everything when I said output level is 2 here. So that transcribes all of these characters into hello. And then it set a rule. This was a rule put out for an overfull box because one thing that I had set in that preloaded option was that every overfull box should get a rule that's 5 points wide. Now look at this rule. It's 14 by 10 wide. That's because it's been magnified twice. So I'm actually getting a rule that's 10 points wide. So if we went over and looked at the hard copy that came off the Dover, we would have seen a rule at the end of the word hello that was 14 points high and 10 wide, and the hello would have been set at 20 points instead of at 10 points. Then it pops, and we go back to the previous level of the stack, end of page, and that was it. So that's the idea of the DVI file for a short program. Time is running out now, so we'll have to break and meet again at 3:30 for our final session.